Hello, good afternoon. Oh, there she is. There's the mancha. All right, awesome. Good to see you, a real person. And there's hello, Tania, to a cross section of a real person. Excuse me. There's Michael, a full real person, although without glasses today. Awesome. And one day we'll learn what bridge that is. I think it's Golden Gate. Whatever. Truth is, oh, maybe it's not. Maybe it's a Arizona. All right. Anyway, good morning, good afternoon, Shen. Good afternoon, Jadith. Good afternoon, Harris. Again, I'm just acknowledging non-black boxes first. And now I'm going to the chat. Hold on, there's more people coming to the chat. Hello, Shen. Good afternoon, Samaya. Good afternoon. Good afternoon, Ms. Morgenstern, about whom I have to admit I'm getting slightly confused. Like, there's like a name. Wait a minute. I think, Ms. Morgenstern, that you have perhaps more than one first. I'm not trying to call you, but I'm personally confused because I think you have one first name in one roster and a different first name in. Hold on. This is my problem. I just want to straighten it out. Hold on a second. I'm just looking because I remember. Hold on a second. Right, like somewhere, sometimes you're Danielle, maybe, and sometimes you're. n- So I want to call you what you want me to call you. So wait a minute. Oh, there we go. No, no. Oh yeah, no apologies necessary. Right, Danielle is perfect. Okay, that's all I want to know. Because okay, totally fine. Just want to make sure I'm not offending you. Okay, and of course, I mean, I'm particularly biased to the name Danielle. And I'm good, Lila. Thank you. Hello, Lila. Okay, there. Now we have a full house. Okay, hello, hello. All right, sorry, I'm out of work. I can't even say hello in a linear fashion. How can I even pretend to teach physics? It's preposterous. So, for example, good afternoon, Luis, and good to see you, Mancha. I'm doing well, thank you. I'm sort of lying, actually. I'm sort of overcompensating. I'm not doing perfect, but I'm doing okay, thank you. How's it going, Harris? I mean, it's going well, thank you, Harris. Um, how am I feeling? I love all these. Yes, I have to open up a portal for people who ask me how I'm feeling. No, that would be inappropriate. I'm feeling good because I'm doing physics with you guys. Aw. Um, no, I will admit, wait, and to Lila and to Tanya and everybody who's asking me, I will admit, wait, and hello, Jerry, and hello, Camille, and hello, Samia. Thank you for laughing. No, no, I'll just admit, just as a disclaimer to myself, like, right, okay, quick personal thing, whatever. Like, I've had two chemos out of six, right? I'm about to have the third one this coming week, which will have interesting implications for your. Well, anyway, this coming week will be number three. I'm only saying that to say, first of all, that probably, well, it does mean I'm out of some classes again. Like next Wednesday, I'll remind you of all this, but next Wednesday it'll be Professor Lou again. But also, I should just admit, so that means I'm getting halfway into the treatment. It is starting. I mean, it has a cumulative effect, evidently. I mean, I guess that's logical. So I'll admit it's starting to have an impact on me. I'm only saying that as an advanced disclaimer or advanced apology that I feel like I'm starting to lose my grip a little bit on like schedule management and sleep management and grading management. I will catch up. It will all come out in the wash, but just bear with me a little bit. But yes, basically, but emotionally, I'm feeling fine and very blessed, and particularly to be with you and to be able to do physics. So let's, in fact, do that. Do I have any other announcements? So we're going to do physics, right? Oh, no, no. Thank you. Thank you, Harris. I appreciate it. Yes. And I'm not trying to drop. Thank you. Noted and appreciated. So as far as physics is concerned, we're just continuing with the material here. Again, as you will have an exam that will be posted not tomorrow, but a week from tomorrow, right? And then it'll be due the following Monday. So I'll make more reminders and announcements and hints about that as we get closer. Like particularly, I guess next Monday we will have class. Maybe next Monday I will be more. In fact, no, I'll guarantee next Monday I'll be more um explicitly. Next Monday what I'll do is things from the practice exam is what I'm trying to say. Next Monday I will be explicitly trying to help you with your exam before you take it. Certainly, that would be a good day to come with any questions um, about the practice exam document. Again, please be warned, during the weekend, I might update the practice exam document, like I might add, because you could either say you're ahead of the material, believe it or not, you might not feel that way, but you're progressing through the curriculum at a fine pace, and your exam's a little bit later than sometimes it is. So again, just quick warning, I may add another problem to the practice exam so that if it's on the real exam, you wouldn't be surprised or unprepared for it. And also don't think, and if I do, if you have that much more to deal with on your practice exam, on your midterm exam, that just means there's less to worry about on the final. Like, I mean, whatever you're doing, it's going to appear somewhere. So don't, it, it all will benefit you in the long run. Anyway, um, what I'm trying to say right now is, as of Monday, I'll be more explicitly talking about your exam and your practice exam. Presumably Wednesday, when you have Professor Liu, however she decides to do it, she has access to your practice exam. She does. I mean, she's in Google Classroom as well, obviously. Um, so she will know that you're having an exam coming up. Uh, however she does it, whether it's board meeting format or discussion or lecture format, on Wednesday, she too will be there to support you and help prepare you for your exam. Okay. All right. So all that said, today I want to continue with, so you should have questions. You should really use that practice document really as your way of studying. And you should come Monday and Wednesday with concerns or questions that you have about the practice document. And again, please remember, the more specifically focused your question, the more efficiently we can answer it and the more of them we can get to in a given class period. Right. I mean, during lecture, we don't do like explicit review session. Like, I mean, this is our way of reviewing. So the more you can come with your own questions and the more specific they are, the more of them we can address in a certain period of time. Okay. So today, so that also includes today. I mean, if you have questions about either the format of the exam or the expectations or the practice document, I mean, feel free to at least put them in the chat today. And if I can't answer, I won't, but I mean, try. So that said, what I want to get back to now is the material, the curricular material, which is waves, the wave equation, specifically the Doppler effect. Okay, everything that you see on this board right here is where I'm heading today. It's not something that I've already said in this class. Those of you who took Physics 203 at John Jay hopefully recognize at least the second block of equations here on the board. They are technically from Physics 203, but we're going to set them up and start using them in order to solve Doppler effect problems regarding wave motion. So today I want to get to this whole Doppler effect business, again, recognizing you've already been assigned a homework about it. You had to struggle your way through on your own without any explanation. Again, I know that. So again, you can, as long as you tried it, you can revise, re-upload for all the points whenever you wish. And again, also, you're not having any new homework for a while until after you get through this exam. So just be aware, again, I realize I'm trying to catch up your headspace in what I'm doing in the lecture now. So this page that you're looking at right now is like where I'm trying to get to today, all in the effort to solve Doppler effect problems. That said, okay, picking up where we were yesterday. I'm just going to switch the view of the screen. Sorry. Picking up where we were yesterday. Okay, what's at the top of the screen here is what we finally established yesterday. What, again, in theory, you sort of figured out or realized in lab 3, at the end of lab 3. What's at the top in yellow is super important. It is the classic one-dimensional wave equation, like this thing at the top in yellow. This is the wave equation. It is a differential equation. It's the second differential equation of this class, right? Differential equations are not a joke. I mean, they're not easy. They're not obvious, but they're real and they're real important. Um, the first, do I want to write this down? Well, okay. So this is a second order differential equation. The other differential equation that you've learned so far in this class, the one that a lot of your midterm is focused on, the other differential equation that you learned in this class was also a second order differential equation. That was the equation for simple harmonic oscillation. These two equations are very similar, but they are not the same. In fact, okay, so I'm going to pause on that. I'm going to set up a compare and contrast on the next page. So, okay, hold on. I'll go back to that page in a moment, but just so we can be as clear as possible here. Sorry. Okay. Like in a really weird way. I mean, we've been saying a lot in this class. I think there's a lot to study. You have a midterm coming up. I mean, I think there's a lot of material to go through. There's a lot of homework assignments, blah, 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 blah. But really, if you were to step back and try to understand everything we've been doing so far in the class, in a way, it all comes down to these two equations. Okay. Like we've had two big topics in this class so far. One is simple harmonic oscillation, and the other is waves. They are super related, but they're not the same. Any wave involves a lot of simple harmonic oscillators, but any one simple harmonic oscillator is not a wave. Okay. Each topic crystallizes down to its own differential equation. So in a way, this whole class, now, of course, in order to understand the differential equation, you have to like understand all this math and what all the symbols mean and everything. So that's like, we've been spending a lot of time unpacking each, but in the end of the day, simple harmonic oscillation comes down to the differential equation that you see on the top of the page. It is a second order differential equation, meaning a second derivative is set up as is expressed as a function as excuse me. Well, yes, a second derivative is expressed as a function of as some kind of function of the dependent variable. The other differential equation, the wave equation, is also a second order differential equation. But one thing to notice right away that's different about it is it's a partial differential equation. The first one is, quote, an ordinary differential equation, an ordinary derivative. The second one is a partial differential. Now, why that? Because the one thing you want to notice right away is in the top case, you have a function of one variable. Y, the dependent variable, is a function of time. Whereas in the second case, whoops, sorry, and I know someone's in the waiting room. Hang on 1 second. In the second case, you have a function of two independent variables. So when we take derivatives of one independent variable at a time, and we call them partial derivatives, right? Okay, again, I'm basically just trying to summarize where we are so far today. I don't mean to rabbit hole. No one ever means to rabbit hole, except for a rabbit, I guess. What I'm trying to say right now is if you want to understand the wave equation, which is what we are dealing with today, we're dealing with that second equation, the wave equation. If you want to picture what it means visually or in English, it's good to compare and contrast it to relate it back to what the original differential equation for simple harmonic oscillation ever meant. Okay, so I'm going to say a lot here. So try to take notes on it or whatever. If you look at that first equation, you look at that first equation. If you look at the first equation, the first equation, it looks very mathy. It is very mathy. What it is, and you should know this for the midterm exam, what that first equation is Hooke's law, just written mathematically. Like really, you know you're learning something or you're understanding something if you can see what I mean. That first equation is really F equals negative kx. Only we substituted k, but we also understand that F net equals ma. So it's really F equals negative kx. What we're really saying in the top equation is negative kx equals ma, but a is d2y dt squared. Practice that. Understand what I'm saying for the midterm exam. What I'm saying is that top equation, what it means in English, it means Hooke's law in English. What it means, if you visualize a mass on a vertical spring, right? A vertical, because I'm using Y here. I could have used X and make it a horizontal spring, wherever. But if you picture a mass on a vertical spring, what that top equation is saying is the rate at which the mass accelerates back toward equilibrium, right? The left side is acceleration, right? Second derivative of position with respect to time. What the left side is saying is the rate at which the mass accelerates back toward equilibrium at any given moment is directly proportional, is in other words, a constant times is directly proportional to y. What is y? Y is the vertical position of the mass. Y stands for how far away the mass is from the equilibrium position. So with the whole statement, I'm talking about the top statement now, the top equation. What the whole top equation is saying is, at any given moment, if you look at a mass that is oscillating harmonically on a spring, you look at that mass at any given moment, what you find is the rate at which the mass is accelerating back home to equilibrium is directly proportional to how far away it is from home, right? This is what, I mean, that's Hooke's law. That is the essence of elasticity. That's what it means to be springy. That's what drives this back and forth thing, that phenomenon that we call harmonic oscillation. I'm going to say it one more time. And the reason I'm saying this is partly to review to help you conceptualize for the midterm, but also because I'm trying to set up a compare and contrast with the slightly more intimidating looking wave equation. So what I'm saying in the top equation, again, the harmonic oscillation equation, I'm saying what it means in English is the rate at which a mass accelerates back to an equilibrium position is directly proportional to how far away it is from the equilibrium position. Go to extreme cases in your mind. If the mass is at the equilibrium, if it's already home, if it's at the equilibrium position, if y equals 0, then it doesn't accelerate at all, right? I mean, it's not pull. The spring doesn't pull it. There's no net force on it. It doesn't accelerate at all. That doesn't mean it doesn't move. It might be moving because it might already be moving, right? But it doesn't accelerate, right? So if a mass is at the equilibrium position, it doesn't accelerate at all. If it's like a meter away, it accelerates back to the equilibrium position at some rate. If it's 2 meters away, it'll accelerate back to equilibrium at twice that rate. That is, right? The greater the displacement from equilibrium, the greater the acceleration toward equilibrium. That's what it means to be elastic. That's what it means to be springy. That's what causes and drives simple harmonic motion, oscillation in time along one axis of space, right? Okay, so the top equation is simple harmonic oscillation. That's like the bulk of your midterm exam, the bulk of the material that we've been studying, like, for months already. Please understand that. Oh, if you made a graph of that, it would be a cosine graph, right? If you made the solution to that equation, it would be, in fact, I almost want to write this down, but I don't want to rabbit hole. Yeah, I'm not going to write this down, but you might write it down in your notes. You might even screenshot your notes and send them to me for points. What I want to say is the solution to that equation is like y equals y naught or a, whatever you, y equals a cosine omega t plus phi plus a phase constant, right? That's the solution. In other words, if you made a graph of where this mass is at any given moment in time, you get a cosine graph. Okay, that's like the mid. Now, notice before I move on, everything I just said about the top equation is about simple harmonic oscillation. Even right up to the end when I said it's a cosine graph. When I say it's a cosine graph, I mean if your horizontal, your independent axis is time, and your vertical axis is position, is y in this case, what you get is a cosine graph. Notice none of what I just said used the word wave. None of that is not a wave. That is an oscillation. The graph of it may be a wiggle, but it is a wiggle that represents wiggling in time. It is not, it's like it's just right, it's not wiggling in time and space. I don't know how to put that better, but that's just oscillation. Now, if we proceed down to the most recent second order differential equation, the differential equation we have now we're talking about waves. Now we're talking about a function of two variables. We're talking about a situation where a long piece of string like lab 3 is at any given moment of time looking like this, at any given moment of time is looking like that, but over time the wiggles are wiggling, if you know what I'm saying. Like, I can't say it better than that, but it's not just a cosine graph, it's a cosine graph that is cosinusoidally wiggling throughout time. It's a wave now, the second equation, right? And what I want to say to you is, what does it mean? And this second equation, the solution to this is not y equals a cosine omega t plus phi anymore. Now it's y equals a, and you might want to write this down, right? The solution to the top one, or a solution to the top one that we've been using, is y equals cosine, excuse me, y equals a cosine omega t plus phi, like plus a constant. That's a solution to the top one. But to the bottom one, a solution is now y equals a cosine omega t plus kx, right? Subtle but enormous distinction. Like now, the phase, extra term, the phase in the cosine is not a constant number anymore. Now it's a function of x. Yes. Good, Nico. Yes. Capital A. Yes. I'll just leave it at that. Yeah. That's awesome. That's total points, like double, triple with sprinkles on top, hot fudge points. Yes. Um, Oh, yes. So okay, so number one, what Nico just for everybody, I'll say it again because it's like so good that someone's paying attention, like not just to me right now, but to the whole deal. So first of all, I'm saying, yeah, the solution to the second equation is y equals, or a solution, the solution we're using in class is y equals a cosine omega t plus kx. And the K, like Nico was saying, is like a capital K, or the way I draw it is like a K with serifs on it. Right. In other words, he's totally right. It's not the K of Hooke's law. Totally different K. It's the K that we now call angular wave number, right? Which I'm going to use. I'm going to start writing this out in a moment. I'm going to do something with it. But it's the K that only comes into play now where we have a wave, not just a oscillator, but a bunch of oscillators, right? So now we have oscillations not only in time, but in space. So now we don't just have an omega t term in the cosine thing. Oh, awesome, Michael. Wait 1 second. Yeah, awesome. Now we don't just have omega t in the cosine anymore. We also have kx. So now the whole deal, before I say any more, before Michael says any more, and then I say any more, the whole deal now that we're in waves is we're talking about cosine oscillations in time and in space. That's what you're trying to see in lab 3 and 4. And so, yes, the K that I'm talking about now. Oh, in fact, the K, I'm sorry, I guess, and then I'll get Michael, like basically what Nico's saying. The K that I mean here is this K, like not the K of Hooke's law, the K of angular wave number, i.e. radians per meter. Okay, I'm gonna pause. So Michael, yes.
I'm wondering what the solution was to the second equation. You were saying like y equals. I didn't write it down. I was writing. You were going a little too fast.
Okay, sorry. Yeah, I'm going too fast. All right. Yes, let me write it. Great question. Let me write it down. I'm just trying to figure out a way that I can write this without rabbit hole, without crowding this. Okay. Yeah, I'm gonna make a new page. Bear with me for a second. But yes, I'll write that down. Okay.
Thank you, Professor.
No, thank you. Great question. No, I love it. I love it. Hold on. So okay. So I mean, this is partly to answer Michael's question, but it's not just Michael. I mean, it's also to explicate what Nico mentioned a moment ago, and just to like summarize this whole thing. And again, all what I'm saying now is, as always, I'm partly just trying to lay out the steps that I need to make the next point in the curriculum to you, but also hopefully this is like a good putting together the fundamental ideas for the exam. Again, and again, of course, in the exam, you have to do a lot more details than this. But if we're trying to get the big picture of what's going on, like to answer Michael's question, like, yes, like we're doing a compare and contrast. First, we had simple harmonic oscillation. It's described by that equation up on the top of this page. And we found that a solution to it is a cosine omega t plus phi. Like phi is just a constant number, right? It was like the phase constant. It's measured in radians. It's how far ahead or behind, one oscillator is in its cycle when we start our stopwatch, right? That's so. And let me back up even further to try to help with the exam. All I can say is this confused me for such a long time. Like I'm continuing to say to you guys, here's a differential equation, and then I say, here's a solution. And I know in homework too, that goes on a lot. It's like, here's a differential equation. Is this a solution or not? It's very confusing at first. It's so confusing, you might not even know you're confused. Like, honestly, it's confusing because it's like going backwards. It's like Jeopardy. Like we give you this equation because what you're used to in science, maybe a lot, even in physics, is you're used to like getting a problem, being asked to find a solution to the problem. So you use equations to get solutions. Like that's what you're used to. Like you plug into equations and you get solutions. But now we're doing this weird thing where we say, here's the equation. What's the solution to it? I'm very sympathetic. If you find that weird at all or confusing, or if it's throwing you off, like, welcome to the club. You're not crazy. Or maybe you didn't even notice you were confused, but you are. It sounds confusing that we're saying, here's an equation, and then we say, here's the solution to the equation. Like you might think, wasn't the equation already a solution? Here's the deal. with differential equations, the reason we talk this way is differential equations by their nature, they always set up, they instead of telling us how a variable depends on another variable, which is what we want, and what a traditional equation is. A traditional equation in a function in math or physics is like, if you tell me the input, I can tell you the output. Like a traditional equation is like y equals 1/2 at squared plus v naught t. You plug in t, what comes out is y, right? That's what we want in physics. That you, where how some dependent variable is depending on some independent variable. With a differential equation, by definition, a differential equation doesn't give you that. It gives you all that information, but packaged in a very unfriendly way. A differential equation says that the rate of change of the rate of change or of some variable is related to the variable itself. It so every time I say solution, I know I'm getting off a little bit in a rabbit hole, but again, because I think I'd rather be talking to people than to myself. So just because Nico and Michael like sort of asked, and I think it's very relevant, indulge me and let me explain that. Like when I write the solution in white in the middle of the page to the top differential equation, or then I write the solution in white again at the bottom to the next differential equation. What I'm saying is, okay, if what you want as a physicist is some way of plugging in the independent variable called time and spitting out the dependent variable, in this case, position along a y-axis, that's what we want. That once we get it, that would be a solution. We need to know a yt or a yxt function that fits, that satisfies, that solves the original differential equation. Again, no, so part of what you're practicing for the midterm and in the midterm is I'm just saying this stuff now, at this point in the curriculum, but part of the midterm is where I wrote that cosine thing in the middle of the page. You would want to show yourself and show me that if you take two derivatives of that with respect to time, if you differentiate once and then differentiate again with respect to time, you would get the differential equation. That's what we're saying. And same thing with the thing on the bottom. To say something is a solution says that, oh yeah, it's a regular everyday function, like one that we could actually use for predicting in physics, but it comes from the differential equation in the sense that if we took two derivatives of it, it would end up being equal to whatever the differential equation says it's equal to. I'm saying too much, but so that's what I mean by solution. Solution is the form we actually want in physics, but it solves the original differential equation, which is what came out naturally by just applying physics laws. Okay, so anyway, I don't know if that helps at all. So, okay, now back to what I was saying before. Notice both of these equations are very similar, but not the same. And both of the solutions are very similar, but not the same. So what I want to say now is the original differential equation for simple harmonic oscillation, what it says in English. I mean, I know I just said this 50 times, but what it says in English, it's the definition of elasticity. It's saying the rate at which you accelerate back to the spot that we call equilibrium is directly proportional to how far away you are from equilibrium. Okay, that's what it means to be a simple harmonic oscillator. Now, what does it mean to be a wave? What does the wave equation say? So, okay, so now I'm back on track here. What does this second equation say? Well, on the left side, it's also referring to acceleration, right? It's second derivative of vertical position with respect to time, just like the top equation is. And then if I'm reading from left to right, then on the right-hand side, it says, okay, equal to, again, a constant. It happens this time to be a positive constant, not a negative constant. That's an interesting detail, but that's just what it is, a detail. But again, it's a constant, like omega is a constant. K is a constant. So omega divided by K is a constant. So if I'm reading from left to right, it says acceleration is, sorry. I'm not trying to say that acceleration is versus concavity. I'm just trying to say, okay. If you read it from left to right, acceleration is equal to a constant times something. Put another way, acceleration is directly proportional to something. Well, like what kind of, okay. So this atop was one oscillator. This here, we're talking about a wave. So picture some point on the wave. Like this is this is a snapshot of some slinky, like in lab 3. Um, that ripples are going through. What I'm trying to say is, if you picture that slinky in lab 3, picture some point on the slinky. What the second equation is saying is the acceleration of that point toward equilibrium is directly proportional to something. But what is the something? It's a little bit more complicated than just the letter Y, right? In the case of harmonic oscillation, it was directly proportional to displacement, Y. Here, it's not displacement, it's a second derivative. Well, it's a second derivative of Y with respect to X. I mean, if you picture a snapshot of the wave, like where this is the X axis, and let's say, this is the Y axis, from math class, if Y is a function of X, and you think of a graph, Y equals a function of X, and you think of the graph, at any given point on that graph, the first derivative of Y with respect to X is the slope of the graph at that point, right? First derivative, we understand graphically, visually, to mean slope, steepness, rate of change of the curve, right? Second derivative is rate of change of the curve. In other words, second derivative is not slope, it's slope of slope. It's the rate at which slopes are changing, right? It's right. So second derivative is not slope. It's not just how steep the graph is at a point, it's how much the steepness is changing. When steepness doesn't change, we have a straight line. When steepness changes, we get a curve, right? So what second derivative really is measuring is what you might call curvature, or what they tend to call in a math class concavity, right? What does concavity mean? It means like how much like a bowl or a bowl something is. It means how curved something is, how not flat it is, right? That's what second derivative. Like second derivative with respect to time is acceleration, but second derivative with respect to space is concavity. Think about that on your own time or meditate on that or whatever. But what I'm saying here in the physics class is, okay, so what that means is to be a wave, to be a wave means that at any and every given point in a medium, we are obeying this equation, the bottom equation, the yellow second equation on the board. What the yellow equation is saying is at any given point in the medium for a wave, at any given point in like a bent slinky that's wiggling back and forth and creating pulses, right? At any given point in that slinky, the rate at which a point accelerates back to equilibrium is directly proportional to how concave the slinky is at that point. In English, the rate at which a point accelerates back to flatness is directly proportional to how unflat, how bent, how disturbed, how curved, how warped, how bent the medium is at that point. It's saying it's saying the same thing as the oscillation equation is saying, but it's saying it now in higher dimensions. I'm going to say this one more way, and then I'm going to move on. But I'm saying that what a wave is the same concept as oscillation, but it's blown up, it's expanded, it's extended, it's deeper, it's happening in more than one. It's not just happening in time, it's happening in time and in space now. So if the concept of oscillation was the farther away I am from a home point, the faster I accelerate toward that home point, if that's what oscillation means, then what wave means is the more bent out of shape I am, the less flat I am, any given point in the slinky. If you put any point in the slinky at any point in space, at any point in time, that a slinky is making waves, what it means to make waves is that any given point in the slinky races, pulls the slinky back to flatness, tries to unbend itself at a rate that is directly proportional to how bent it is at that point. Where does the slinky want to be? It's not one that it wants to be at a spot the way a spring does. There's no special spot that the slinky wants to be. There's not even a special height that the slinky wants to be. The equilibrium is no longer a location. Look, equilibrium is now an orientation. It's an x-axis, not meaning it's this particular height, meaning what the slinky would be at equilibrium is just flat, right? But there's places in it that are bent, that are disturbed. And those places we recognize in any given moment as crests or troughs that are pulsing back and forth, right? Well, how do they pulse back and forth? What's going on? The idea is that they are restoring themselves perpetually, just like a spring is trying to restore itself perpetually to home base. With a wave, home base is no longer a base. It's not a spot, it's not a height, it's not a place. It's a shape. The spring, the slinky wants to be flat. So at any and every given moment and in every and any given location, any not flat parts of the spring race towards flatness, accelerate towards flatness at a rate that is proportional to how not flat they are. I mean, honestly, I think that is so cool. I mean, you don't have to, but you could. I mean, I can't lie about this. Like, it's once you get it, it's literally the concept of oscillation restoration, but blown up. We're not trying to race to a place. We're trying to race to a shape called flatness. So the equation totally captures that. It's saying the rate. So it looks very intimidating, perhaps, has all these squares and second derivatives, but it's really just a linear equation, just saying any given spot, the rate at which it accelerates back home to flatness is directly proportional to, excuse me, directly proportional to how not flat the, the spring is at that point. So waves are continuous disturbances that are continually undisturbing themselves, constantly trying to be. That's okay. That's the best way I could say that. Put in the chat if you don't know whatever. So that's the second. That's the wave equation. That's what it means in English. Acceleration is directly proportional to concavity, as opposed to acceleration is directly proportional to displacement. Okay, that's what that means. Now, what does that have to do with the Doppler effect or anything? Well, the term in the middle, so I keep saying the left side is directly proportional to the right side. Why do I keep saying that? Because the left side is equal to a constant times the right side, right? So back to this page now. That term in the middle, the omega over k squared, is a constant of proportionality, right? I mean, it's like m in y equals mx plus b or something, and here b is 0. So my question now is, okay, I've spent all this time explaining what is proportional to what. Now let's talk about that constant proportionality. I mean, is it just a random number or just a random thing? I mean, it is a constant. Omega is a constant, k is a constant. But like, what do they mean? What does that signify? Well, recall, I just lost my train of thought completely. Okay, so I'm trying to unpack like what does it mean, omega over k? So omega is angular frequency, right? It's 2 pi per the period, right? I mean, there's many different ways to say omega. And again, this is like quick. I don't know if this is review or checkpoint for the exam, but like I'm just going to use these concepts now because we're moving on. But like, if you don't know why that's true, that omega equals 2 pi over t, or you don't know what it means, right? T is period. Omega is angular frequency. There's 2 pi radians per every cycle. Like you want to meditate on that. Like all I can say again in terms of the exam is like the simpler something seems, probably the more important it is, and probably the more time you should spend thinking about it. Like don't confuse simple for easy, if that makes sense. They're not the same. So, like, you should go home and make sure you understand why omega is cycle. Omega is radians per second, right? It's how many cycles you do every second. Only we're measuring cycles in radians, and we're recognizing that there's 2 pi radians in every one cycle. Okay, I'm overspeaking it. The point is, omega angular frequency is cycles per time. Yes, 2 pi. Okay. Similarly, K, the thing that Nico was, highlighting before, K is angular wave number. It's number of cycles per length, per space. I don't want to confuse this, but hopefully this helps. Right? So K is to space as omega is to time. Omega is how many cycles do you fit in a given unit of time, i.e., how many radians do you fit in a given unit of time? K is how many cycles and or radians do you fit in a given space? The space, the amount of time of one cycle is called period. The amount of space for one cycle, like the amount of meters from one crest to the next crest, is called wavelength, right? Both are involved if we're talking about waves. Again, let me say, only the first concept is involved if we're talking about simple harmonic oscillation, but both concepts are involved once we're talking about waves. Waves are oscillations in time superposed on oscillations in space, right? Okay, so both are involved. So therefore, so therefore, omega over k is lambda over t, is wavelength over period. So what? Think about it. Omega over k, I'm saying, is the same. You could write it as lambda over t. And who cares? Like, why do you want to write it a different way? Because if you stare at it that way, it may become more evident what it is that we're writing down. I mean, lambda is the number of meters per cycle. T is the number of seconds per cycle. So what we've just written down here is how far it is. So picture you're standing there, your partner is like you have the long slinky in lab 3. Your partner is shaking up and down one end of this long slinky. So crests and troughs are like propagating back and forth, right? So if you're standing there watching, a crest is coming in toward you, like you fix your eyes on a crest coming in toward you the from or a full cycle, I mean, like from crest to crest. So the full length from one crest to the next is like say 3 meters, and it's coming towards you this 3 meters. And the amount of time, excuse me, the amount of time from one crest to the next is say 1.5 seconds, right? So a crest comes to your eye, and then a second and a half later, then the whole wave has advanced 3 meters and the next crest is at your eye. So what does that mean? It means the whole series of pulses, the whole propagation is advancing like a full 3 meters every 1.5 seconds, right? Meters per second is speed. This whole thing is the pulses are propagating back and forth, in that case, in that example, at 6 meters per second, right? What I'm saying is the amount of meters for a full cycle divided by the amount of seconds for a full cycle is the rate at which a full cycle, a full phase, flows forward or backwards through the medium. I'm saying this. Okay, I'm saying that omega over k, which could be expressed lambda over t, which could be expressed yet one more way, which I will in a minute, is v, where v is speed. Speed of what? Speed of propagation. Technically, on the web or in Khan Academy or in like textbooks, this is technically called the phase velocity of the wave. It is the speed of the wave itself. It's the speed at which the wave crests, the wave troughs, the wave pulses are flowing through the medium, like along the x-axis. This is the immaterial speed. This is the very important. This is the speed of the wave. I don't want to overcomplicate it. I mean, it's the speed at which the wave is traveling. But what I mean is, it's not. It's not the y-axis. It's the x-axis. It's not the speed at which any given oscillator is going up or going down. Like that is a concept. That's a thing. But as you learned all over and over in homework 1, each one of these oscillators that's making up the wave is changing its speed every single moment. It has acceleration, and it's changing its acceleration every single moment, and then it's changing its change in acceleration, like it's jerk. Like in terms of the y-axis, in terms of the thingy things that are oscillating up and down, all of those particles that constitute the whole medium, each one of them has continuously changing position, velocity, acceleration, jerk, whip, etc. Right? All of that is beautiful but super complicated perpetual change. But all of those particles put together in this way creates a flow that goes on an entirely separate axis. This flow, this wave, this propagation, this pulse, this thing is a thing, but it's not a thingy thing, right? Like we now see a wave going back and forth horizontally. We see crests and troughs going back and forth horizontally. What are we seeing? We're seeing disturbances in a medium. We're seeing shapes. Like we're like, oh, there's a crest. Like there's a slinky that's bent in a certain way. And then we watch as the bend goes this way. please remember again, what's fascinating about this, I mean, at least to me, and maybe what's hard about it until you get used to it, is what you're tracking with your eye and what you're treating with physics equipment and physics equations is not a material object, right? There's no piece of metal that's like going like this. There's a shape, like first it's a piece of metal that's over here and then it falls down, then another piece of metal that goes up and then it falls down, and then another, right? So what's flowing is immaterial. It's non-particular, but it has a rate of speed. And apparently, in fact, it has a constant rate of speed. That rate of speed, sorry, that's so the rate at which the immaterial pulse is flowing along the x-axis, that rate of speed is omega over k, or put another way, or lambda over t, or put one last final way, sorry. Remember, we have all these different, remember, I've said from the start, you can express frequency one of three different ways. They're all equivalent. You could talk about omega, you could talk about F, or you could talk about T, the period. They're all equivalent. They're different. They're all true, but they have different, they have different utilities for different contexts. So before I go any further, if you understand what I'm saying, that omega over k, that proportionality constant, is the speed of the wave. You could see that by expressing it as lambda over period, or sorry, or the way you could express it is, and this will come up a lot in instrumental, by the way, and PChem. When you take PChem and instrumental, you'll see a lot in textbooks and stuff. A very common way to express the speed of a wave is wavelength times frequency. Like that may not be the most intuitive way to say it, but it's the most common and useful way to say it. Speed of a wave is wavelength times frequency. Let me write this. Sorry, this is getting too cramped. 1 second. Okay. So this is a memory. This is a takeaway for like future life. V equals lambda F for any wave. Any wave. The speed of the wave is equal to the wavelength of the wave times the frequency of the wave. This means that as long as you believe that the speed is constant, as long as you hold V fixed, then if the wavelength goes up, the frequency goes down. And of course, actually, if you really think about it, that is intuitive and that is your experience. That is when you're doing lab 3 and you're making waves go back and forth on a big slinky. If you start shaking the spring more rapidly if you make higher frequency waves, you notice automatically what happens is the wave pulses get closer and closer together. They get shorter in space, right? If you make F greater, you automatically find that wavelength gets shorter and smaller and vice versa, assuming, right? So that's a thing. Like wavelength and frequency are inversely proportional for a given wave, assuming that the speed of that wave is constant. Is that a fair assumption? In other words, do we really not have to deal with acceleration and stuff once we're dealing with waves? Yes, we don't. Is the speed of a wave constant? Very important. And I am watching the clock. I know we have 13 minutes left. Very important and subtle point here. Let me backtrack first. So what it says is the speed of a given wave constant? Yes. W and K are parameters. So the speed of a wave is constant relative to its medium. So what am I saying? Remember this whole business of parameters. Remember a simple harmonic oscillation. And I'm going to say this fast. You should write this down if you can. But remember, with a simple harmonic oscillator, omega, like for a mass on a spring, a mass of M on a spring of stiffness K. Remember, omega was in that case square root of K over M, right? Or if you had a pendulum in the lab, omega was square root of G over L. Like, remember in other words, what omega was not was in any way dependent on amplitude. What we made a big deal of saying was, oh, once you know the material properties of this oscillator, once you know how heavy the mass is and how stiff the spring is, then it doesn't even matter how you set it up. If you know in advance it's this heaviness on this stiffness, then omega equals square root of K over M. You automatically know at what rate the mass is going to oscillate back and forth. That's why we said simple harmonic oscillators are clocks. They oscillate at a certain rate in time, regardless of how you set them up in space. Very important aspect, defining feature of simple harmonic oscillators. Now, put a bunch of oscillators together, spread them all out, and set them up so that they're all out of phase in accordance with a given K, right? So now you know in advance the rate at which, so you know the material properties of this vast collection of oscillators that you just set up. The word for a vast collection of simple harmonic oscillators, as long as they're oscillating in a certain phase staggered way, we call that a medium, right? This is the medium now. The medium is the vast collection of oscillating particles. The medium is that material collection through which the wave will propagate through which the wave will propagate. So what I'm saying is apparently take that idea about oscillation, we said if we know the ingredients of the oscillator, if we know the parameters, we'll automatically know the rate it's going to oscillate. Now I'm saying, well, if you put a bunch of oscillators together and create a medium through which wave pulses can flow, if you know the material properties of the medium, if you know what type of oscillators it's made up of, and you know how they're, arranged, then no matter how you start, or no matter what kind of disturbance you initiate to create this wave going through, if you know the material properties of the medium, then you automatically know the rate at which each piece of the medium will oscillate. Therefore, you automatically know the rate at which the pulse will propagate. In other words, as long as you fix your medium, you have fixed the speed of the wave. The speed of the wave is constant relative to its medium. If the medium doesn't change its properties, then the speed of the wave won't change. That's why people can talk about the speed of sound as though that is anything, as though that means anything, as though it's a number. Well, it does, and it is. Like, no one talks about the speed of a baseball. I mean, you could talk about the speed of a baseball, but we don't say like the speed of baseball. It's like, what? I mean, if I pitch a baseball, it goes 75 miles an hour. If Nolan Ryan pitches a baseball, it goes 105 miles an hour, whatever. You know what I'm saying? Baseballs go whatever speed, cars go whatever speed. But apparently, apparently waves go a certain speed. Yes, they go a certain speed in a certain medium. When people say the speed of sound, what they really mean is the speed at which sound would propagate through air, if assuming air is at standard temperature and pressure, for example. Like, once you specify the medium, then the speed of the wave is fixed. Now, that is a tremendous feature of waves and makes waves so useful and reliable and fascinating. It's not a feature of particles. It's a feature of wave motion, that the speed of a wave is fixed relative to its medium. Now, I only have 8 minutes left, but I have to remind you what I mean by relative to. Yeah, okay. Quickly, like, what I'm about to say is a reminder from in Principle Physics 203. Now, I'm sorry. I'm looking at the chat. How much did I miss? It was a million years ago. I'm so sorry. Yes, okay, sorry. Direct chat person from like a million years ago, 20 minutes ago. Omega over K is the velocity. Yes. Although one thing, oh, and totally, and also Lila a million years ago. Yes, it's totally what we did in lab 3. Yes, thank you. Yes. Awesome. And yes, person in direct chat. So omega over K is just the velocity. Yes, but I just want to kind of modify that word just. Like, yeah, it's just the velocity, but that's like a huge deal. Okay. I mean, it's like a big deal that it's the velocity, but yes, the answer is yes. Now, but what I'm trying to say now is remember from Physics 203, even if you didn't have me, now I tend to really emphasize the thing I'm about to say in Physics 203, and I understand the other professors don't necessarily emphasize it to the same degree, fine. But a big lesson of Physics 203 is supposed to be is Galileo's principle of relativity, and there's a million different ways to say that. Oh, sorry. Cool. Thank you, direct chat person. Yes. No, it is really cool. Thank you. Yes. Sorry. Quick. No. Okay. Yes. I mean, if I had to end right now, like, right. Thank you for noticing how cool it is. Like this equation right here, the second one, or really the second one on this page, This equation right here, I mean, this is an unbelievable equation. Really, like, and if when you're looking, if you're like me, I mean, God forbid, work forbid for you, but believe me, when I first saw that equation, it meant nothing to me. Please don't think that just because I love physics and I do physics all the time, that means I was born like automatically understanding these things, or don't think I didn't struggle. When I first saw that equation, it was gibberish. If that looks like gibberish to you or looks scary to you, like I'm with you, like join the I understand. But I'm saying the more you look at it, the more you look at it, the more you practice calculus, and the more you unpack second derivatives and blah blah, the more you see that equation is unbelievable. How much information is being packed into such a tight, simple package? I mean, I'm getting off the, but yes, like that equation says acceleration is directly proportional to concavity, and the constant of proportionality is speed squared. In other words, I guess to respond to the direct chat person, that equation right there, once you understand it, can be rewritten this way. I mean, I probably should have done this before. Thank you, direct chat person. Like I'm saying, every aspect of a wave is packed into that one equation. What's going on this way, what's going on in space, and what's going on with the flow. It's all packed into that one linear statement. Anyway, so great point, great point. Now I know I'm running out of time. What I want to quickly say now, and look, I am going to run out of time. So what I'm not going to be able to do right now is totally walk you through a Doppler effect problem like I've been sort of, like I eventually will. I'm not going to walk you through step-by-step a Doppler effect problem today. I will eventually, but I'm trying to set it up for you and get you to see how to do the Doppler effect problem. So the one thing I want to say for right now is remember velocity. Remember from physics 203, velocity is not a property that a single object ever has in the universe, in physics. Like no object has a speed. Like even though we spend all this time talking about speed and velocity and all that, the point is an object does not have a speed or a velocity. An object has a velocity in relation to some other object. And it's all, velocity is always a comparison. It's always a relational thing. And it totally depends what you're comparing to what. Planet Earth has a velocity of nothing compared to planet Earth, but it has a velocity of 65,000 miles an hour compared to the sun, and it has a velocity of 650,000 miles an hour compared to the galactic center. Which one of those is the correct comparison? None of them, or all of them. It just depends on what you want to compare it to. They're all true, right? This is the essence of physics. Velocity is a relation between two objects, not a property of one. That means when I say, now I understand I only have 2 minutes, so I'm just going to say this and we'll close on this point. With like 1 minute left or 2 minutes left, where the Doppler effect is coming into play, like the context for the Doppler effect, what is this idea that, wait, velocity is always in relation to something. So when you talk about waves now, when you make a wave, the velocity of the wave is fixed by and to its medium, right? So that means, like if I shout, sound comes out of my mouth and is automatically going 340 meters per second relative to the air. Okay, fine. What's the big deal? Well, the big deal is I'm not air. The big deal is I could move relative to air, or you could move relative to air, and then the sound is going to be doing something very different to you or to me. More specifically, put it this way, and I'm just going to leave you with this. If I throw a baseball at 85 miles an hour relative to me, that means I have a certain arm strength. I throw a baseball. No matter what I do, the baseball leaves my hand at 85 miles an hour relative to me. So even if I stand on top of a subway car and the subway is going past you at 60 miles an hour, right? I stand on top and throw the baseball. Well, then the baseball will go 85 miles an hour relative to me, plus the 60 miles an hour of the car relative to you. So the baseball will go 145 miles per hour relative to you, right? In other words, it'll always be ahead of me by 85 miles every hour. I'm not going to catch up with it or anything like that just because I'm on a subway. The whole thing will move. But I know that the time is, but if I stand on a subway and I shout, so the sound comes out, or I get into an airplane and I shout, so the sound comes out of me 340 meters per second relative to the air. It's relative to the air. It's not relative to me. So if I'm in an airplane and the airplane is going 100 meters per second or 200 meters per second, that means I'm catching up to the sound. Right? That's what I'm trying. I mean, in other words, if I went fast enough, if I went 340 meters per second, I'd be right there staying with the sound. And if I went any faster, I'd go ahead of the sound. I'd pass the sound, and that's called a sonic boom, right? You can't do that with a baseball. You can only do that with waves because waves go at a fixed speed relative to their medium, and the source of the wave could move through the medium. And that's what gives rise to this thing called the Doppler effect. But okay, thank you for being so patient. We'll get to that obviously next class or whatever. But thank you. Just leave it at that for now. Have a good weekend. I'm staying here for any questions or anything, but I'm turning off the recording. So have